In this video, we have a look at what domain and range means and how you can find it depending on a given rule or a graph. So let's first of all look at some definitions. The domain represents the values which can be entered into a relation. For example, the numbers that you can actually put into a rule. Now an example here is y equal the square root of x. If we're considering only real numbers, which we will do in this video, the only numbers that we can input into that particular rule or function, square root of x, are non-negative numbers. So that means that we can have x equaling 0 or x equaling any positive number, but we can't actually have a negative number enter into that square root. So the domain for that function is x being all real numbers which are greater than or equal to 0. Once we've decided on a domain, we can then look at the range for a particular rule or a graph. And in simple terms, the range are the numbers that come out of the rule. In other words, once we've substituted numbers into the rule, anything that can come out represents the range. Let's have a look at a simple example now with a set of points. Now in this case we have 3 points. We can identify the domain as all the x values. They're the numbers that can go into a particular rule. So in this case 3, 5 and 1. The range in this case are the y numbers, in other words what comes out. So we have a repeat there of the number 1. So our range is -2 and 1. Let's have a look now at the domain and range for some specific functions. In this case we'll have a look at the linear function of the form y equals mx plus c. And our first graph is y equals x. So if we follow the line on this graph, we can see that it extends for positive x values to infinity and also negative x values to infinity. There's no restriction as far as the x numbers we can put in. And likewise the y numbers also extend to positive infinity and negative infinity. So there's no restrictions on the numbers that we can put in along the x-axis, and there's no restriction on the numbers that can come out, which we can see on the y-axis there in red. So we write the domain as x values such that, that's the 2 dots, x is an element of the reals. So that notation there, we have x, a little curly c with a line in the middle of it representing an element of, and the capital R with 2 vertical lines on the left represents all the real numbers. And the same applies for the range. It's y numbers such that the y numbers are an element of all the real numbers. Let's have a look at another linear graph, this time y equals 2x minus 3. Now once again we can see that if you look at that red line representing the line graph, we can have x values along all the positive x-axis, and likewise we can have values along the negative x-axis. There's no restriction in terms of what we can put in. And in terms of what comes out, it could be any positive y number and any negative y number as well. Again, the red line indicates that we have that extension for the graph in both directions, positive and negative for x and y. So we express the domain as the x values such that x is an element of the reals. And likewise, the range is equal to all the y numbers such that the y numbers are also element of the reals. So it appears as though that with linear graphs there's no restriction on the domain and range because you can put any number you like in and any number comes out. Well, there are some exceptions. Let's have a look at a couple of exceptions that occur with linear graphs. Our next example has the graph y equals 3. Now along this horizontal line we have points with positive x values and points with negative x values. So there's no restriction on the x values. That means that our domain can be defined as x values such that x can be an element in the reals. Basically saying that x can be any number at all from negative infinity to positive infinity. Now along that horizontal line, every single point has a y value of 3. There is no variation. So the range is equal to y such that y is equal to 3. We can also classify that by just saying the range is equal to the number 3. In our next example we have a vertical line x equals 2. So all the points have an x value of 2 on this particular line, but the y values can be extended to positive infinity and negative infinity. So the domain is equal to all the x values such that x is equal to 2. Or we can just define that as a domain of 2. The range is all the y values such that y is an element of the reals. In other words, it can be any number from negative infinity to positive infinity. Let's have a look now at the domain and range for quadratic equations. In this first example, we have the basic parabola for y equals x squared. Now the points on this graph shown in the parabola in red have x values extending to positive infinity and to negative infinity. But because the equation is a squared, that means that the resulting points for the y values are always going to be positive in this particular case. So 0 is the smallest value for y because that's 0 squared, and everything else is going to be in the positive direction. So the range can be expressed as y values such that y is greater than or equal to 0. So we're only going to have positive values because we're dealing with the squares of the x numbers. Or you can express that as y is an element of the reals such that y is greater than or equal to 0. In other words, it can be any number which is greater than or equal to 0. The domain in this case is expressed as an x value such that x is in the reals. So in other words, x can be any number from negative infinity to positive infinity. In this next example, we have a parabola which is congruent to the one from before. It's just been moved to the left 2 units, which you can see within the equation. It's x plus 2 in brackets all squared. So the domain for the graph here is the same. It's basically any x value where x is an element of the reals. Now with the range, we can see the graph still has only y values which are 0 or greater than 0. So we can express that range as y values in the real numbers such that y is greater than or equal to 0. In this next example, we can see a parabola that, compared to the original y equals x squared, has undergone a couple of transformations. It's been moved horizontally 2 units to the left, and we can see that in the equation because we have x plus 2 in brackets all squared, and it's been moved vertically 4 units in a positive direction. So the turning point is now negative 2, 4. We can see from the graph itself that any x value is possible. So as far as the domain is concerned, we can go from negative infinity to infinity. For the range, because the turning point is now negative 2, 4, the lowest y value is 4. So we can express the range as y being a real number such that y is greater than or equal to 4. And as said before, the domain is x such that x can be any real number. Let's have a look now at the domain and range for cubic functions. And we'll start off with the basic cubic y equals x cubed. Looking at the graph, we can see that we can extend this for x values to positive infinity or x values to negative infinity. And likewise, y can extend from negative infinity to positive infinity. So we have no restrictions here on the domain and range for this particular graph. So we can express the domain as x values such that x can be any real number, and the range is the y numbers such that y can be any real number. Let's have a look at a cubic function now that involves terms other than just x cubed. Now we can see from this graph that we have 2 stationary points. As we look left to right, there's a maximum and a minimum. But that doesn't alter the fact that the graph can extend to positive infinity and negative infinity for y, and likewise for x to negative infinity to positive infinity. So our domain is still the same as before. It's x such that x is an element of the real numbers, and likewise the range is any y number such that y is an element of the real numbers as well. Let's take a look at the domain and range for reciprocal functions. We can see here we've got the basic reciprocal y equals 1 over x. Now not shown on the graph is the asymptotes which exist along the x-axis and the y-axis. Now they're significant because that means that along those particular lines we have undefined values. So the graph is undefined at y equals 0 because no point exists where y equals 0. And likewise the graph is undefined along the vertical asymptote where x equals 0. In other words, there are no points on that particular line. So the domain and range are restricted by those asymptotes. The domain can be x values which are real, and we can see that from the graph. It can extend to negative infinity to positive infinity, but x can't equal 0. And the reason being is because we can't divide by 0 in the fraction where we have 1 over x. Likewise for the reals, it's any y value which is a real number, such that y cannot equal 0. In our next example, we have a transformation which has occurred to the original reciprocal graph. What's occurred here is that we can see in the denominator we've got x minus 2, and the graph has moved horizontally 2 units to the right. So our asymptote now is at an x value equal to 2. In other words, we have no points defined where x equals 2. So the domain is x in the reals, but it cannot equal the value of 2. Because the graph has been translated horizontally, that means the range is still the same. It's any y value amongst the reals such that y cannot equal 0. And that's because the horizontal asymptote hasn't moved from the value of y equals 0. Before we have a look at the next reciprocal graph, let's have a look at the domain and range from an algebraic context. Now with this equation, we know that it's going to be undefined if the denominator is equal to 0. So we know that x minus 2 cannot equal 0. Now that means that x cannot equal 2. When we consider the range for this function, we need to acknowledge that the original fraction, in other words 1 over x, or in this case 1 over x minus 2, is undefined at y equals 0. That's where there's a horizontal asymptote. Now what we have here though is a vertical translation. We can see at the end of the equation we've got a plus 1. So that means that our asymptote will effectively move 1 unit upwards, meaning now that y is undefined at a value of 1. Let's have a look at a graph now of this same function and we'll see how that compares with the results that we've found in terms of the domain and range. Our equation for this graph has x minus 2 on the bottom line, and that will indicate a horizontal translation 2 units, and the plus 1 on the right hand side indicates a vertical translation 1 unit upwards, and that's reflected in the graph. So we can see that our horizontal asymptote is at y equals 1, and our vertical asymptote is at x equals 2, and that's going to give us the x and y values that are undefined in this particular case. So our domain is all the x values in the real numbers, such that x cannot equal 2, as indicated by the vertical asymptote. And the range is all the y numbers in the reals, such that y cannot equal 1. And again, that's indicated by the horizontal asymptote. Let's have a look now at the domain and range for the square root function. We can see here we've got the basic graph, in other words, y equals the square root of x. Now, by definition, the square root of a negative number for reals is undefined. So we can see here on the graph, everything left of 0 on the x-axis is undefined. It won't be part of our domain. Whereas we can find the square root of 0 or numbers greater than 0 along the x-axis. So our domain is all the x numbers such that x is a real number and it's greater than or equal to 0. And likewise as well, we can see with the range or the values on the y-axis, they start at y equals 0 and move upwards. There's no values for y which are negative. So our range is also all the y values which are reals such that y is greater than or equal to 0. In this next example, the original square root function has been translated 2 units to the left. And that's evident from the equation. We can see we've got plus 2 inside the square root sign, and we've got a movement 2 units along the x-axis, such that now our smallest x value is negative 2. So our domain is x such that x is a real number, and x is greater than or equal to negative 2. Now in terms of the y values, we can see that y is still greater than or equal to 0 on that graph. There's been no vertical movement. So the range is all the y values in the reals such that y must be greater than or equal to 0. Prior to looking at the graph for this function, let's have a look at the domain and range in an algebraic context. Now we know because of the square root sign that x plus 2 must be greater than or equal to 0. So that means that x must be greater than or equal to negative 2. We also know that with the square root sign that basic function must produce a y value greater than or equal to 0. But we have a change occurring. Outside of that we've got minus 2. So that means that y must be greater than or equal to minus 2 in this case. Let's have a look at the graph now to see how this compares. We can see because of the function we have a horizontal translation 2 units to the left, and we've got a vertical translation 2 units downwards because of the minus 2. So that means that our initial point, if you want to call it that, has a y value which is at negative 2. So our range is all the y values in the reals, but we can see that they must be greater than or equal to negative 2. Likewise with the domain is all the x numbers in the reals, such that x must be greater than or equal to -2. Let's have a look now at the domain and range of some basic trig functions. First of all, we'll have a look at y equals sine x. Now there are no restrictions on x in either the negative or positive direction. So that means that x can be any real number. So our domain is x such that x can be any real number from negative to positive infinity. But we can also see the range is restricted between -1 and 1. So the range is the y numbers which are real such that it's between -1 and 1. That notation is basically saying that y is greater than or equal to -1, which we can see from our graph, and also y is less than or equal to 1. Again, we can see that from the graph indicated there in yellow. And the notation we have is basically saying y is in between -1 and 1. In our next graph, we can see that we've got the equation y equals sine 2x, and we've increased the number of cycles by a factor of 2. In fact, that's evident because in our equation we've got 2x. And the x values still extend from negative infinity to positive infinity. So the domain is unchanged. It's x such that x can be any real number. As for the y numbers, we can see they extend to +1 and go down to -1. So the range is still y such that y is in the reals, and it's between -1 and 1. So no change in the domain or range in this particular case. In this example, we've added 1 to y equals sine 2x, and that's resulted in a vertical translation. So now y is defined between 0 and 2. So our range, like before, is all the real numbers, but this time y is between 0 and +2. And likewise again with the domain, there's no change. X can be any number such that it's one of the real numbers. The next graph is for the function y equals 3 sine x. So the factor of 3 out the front of the equation means that our y values extend from 3 down to -3. And as such, our range now is all the y values which are real such that they're between -3 and +3. As before, there's no change with the domain. The domain can be x such that x is any real number. Let's have a look now at the graph for the function y equals tan x. Now because it is a tan graph, we know that it is undefined at certain values of x. That's where asymptotes occur. So one of the common ones we deal with is tan of pi on 2 in radians, or it's tan of 90 degrees. That's an undefined value. So when x equals pi on 2, or in fact multiples of pi on 2 such that those multiples are odd multiples, the graph is undefined at that particular value of x. So that's pi on 2. The next one is 3 pi on 2. And that occurs also in the negative directions as well. So our domain is x being any real number, but we do have the restriction as well that x cannot be an odd multiple of pi on 2. And we'll show that here with n pi on 2, where n is odd. But we can also write n as 2k plus 1. And the reason why we do that is because if k is any integer, 2k makes it even, and then adding 1 makes it odd. So that's just another way to define the number as an odd number. As for the range, y can be any number with tan graphs, so we define the range as y such that y is any of the reals. And that of course can be from -infinity to +infinity.